Drag is resistance to motion due to fluid flow. So this could be air, water, mud, etc., whatever. So it has 3 different types. So there's drag that's due to form. So that is size and shape. There's also skin friction drag, which is due to the fluid viscosity. And there is wave, which is like shock wave. And then there is, so all of these are considered like real drag. And then there's a 4th kind that's induced drag, and that's lift. So generally the induced drag is desirable. That's why you induced it. But both of these, the CD0, the CD1, combine into one drag coefficient. So the drag coefficient is going to be different for every object because it depends on all of these things. Now, drag coefficients are generally stuff you can look up in a table, same thing as friction coefficient. But they're usually determined experimentally and they kind of depend on speed. So as speed increases, air compresses, but the air compression is negligible when you're at less than 200 miles per hour. So sound is about 100 miles per hour. So as long as you stay like less than half the speed of sound, then you can use some of these equations. So the drag force FD equals CD, which is the drag coefficient, times 1/2 rho V squared times A. So if we define each of these things, this is drag coefficient. You look that up in the table. This is fluid density. So for air, rho of air equals 1.225 kilograms times meters cubed. Sorry, kilograms per meter cubed. And then for water, this is about 1,000 kilograms per meter cubed. So you can see here, like just based on the fluid densities, if you have the same object traveling through air versus through water, it's a lot harder to push it through water. So that is because some of the drag is due to the fluid viscosity. Now, this V, this is the relative velocity of the object and the fluid. So an example is if you have a static fluid, say like you have a person who is swimming in a swimming pool. Well, the person is moving, the swimming pool water is basically not. So the V that goes into this equation would be the velocity of the person. Now, in a different example, let's say you have the person who's standing in the water at the beach and the waves are coming against them at a certain velocity. Then you would have to use the wave velocity. Now, since it's relative velocities, then if the person started walking against the waves, then you have to add those two velocities together because it's velocity of fluid relative to velocity of person, okay? If you think about like, it's gonna be harder to go faster, so just add the velocities. That creates more drag. And then finally, A is the frontal area. of the object. So that is basically the two-dimensional view of the object, what that area is. So example of that, let's say we have a truck. So the truck, it has some wheels on the bottom. It's got the front, and then it's got the windshield here. Now, when you look at the truck, you basically can approximate its area as this box, H by W, because that is the two-dimensional view. Okay, the wheels don't really make a big difference, but the point here is that even though from the side, the front sticks out more, the frontal area is that two-dimensional view of it. So W times H. Now we'll look at some common drag coefficients. So for a car, CD would be 0.2 to 0.3. Normally for a convertible, it's a lot higher because it's not smooth. It has a rough surface, you know, like there's not as much, there's no car roof, so it just hits the people. That's 0.6 to 0.7. And then a bus is also pretty high, 0.6 to 0.8. Truck, 0.8 to 1.0. Now some things that are low, so like an airplane wing, that should have really low drag because we want the plane to, you know, be able to go as fast as possible, and we really want it to lift instead of drag. Then that is 0.15. And then a person has a lot of drag. That's 1.0 to 1.3. So the drag coefficient can be greater than 1. Now, person on a motorcycle, that is really high, 1.8. And if you think about it, that makes sense, right? Because like you feel the wind really bad on a motorcycle. That's why they have to wear the leather jackets and the masks and all that, because there's so much drag force on them. Now, here's the derivation of how we get to drag force. So we know sum of the forces equals mass times acceleration. You can say that equals mv dv ds, which is, from the drag force equation, 1/2 rho CD A times V squared. Except because drag is a non-conservative force, similar to friction, it's negative because it goes against the motion. So we separate and integrate here. Then we'll have m times 1 over v, because there's a v on each side, so it cancels, times dv equals negative 1/2 rho CD A ds. So we integrate here. So this mass is constant, so we just go from v initial to v. And then here we go from s initial to s. So this is initial position to final position, initial velocity to final velocity. So then if we actually do this integration, we get m times natural log of v over v initial equals negative 1/2 rho CD A times S minus S initial. So you see here, this is a natural log function, so velocity and position do not linearly relate to each other. So, and you can tell this, right? Because as you, like if you're driving in a car and suddenly you stop pressing the gas, the car is going to slow down. So but the drag force on it is going to be really high when you're moving very quickly, and then it's going to be really low when you're almost not moving at all. So you'll slow down kind of slowly. We'll keep going with this and then look at how that plays into the relationship between speed and position. So if initial position equals 0, so you start at the start, and let's see, then we can say that m times natural log of v equals m times natural log of the initial minus 1/2 rho CD A times S. Okay, so remember that this is just from our natural log days. ln of v over v initial equals ln of v minus ln of v initial. That's just a thing to remember. So if we want to get rid of, well, first we need to divide, we want to get v by itself, figure out how is v a function of position. So we can scratch that, divide by this. And then the next thing we have to do, if we want to get rid of the natural log, is we have to raise each side as an exponential. So we'll have e to that power, e to that power. And then we get v equals exp, which is the exponential function, of natural log the initial minus 1 over 2m times rho CD A S. So really, this is going to be like an exponential curve. And then if you want to see like how far, or if you want to solve for the stopping distance, like how long does it take you to get to 0 speed, you actually can't do it, because in the absence of any other forces besides the drag, you'll never actually reach the 0 speed. It goes like this. So you just have to pick like how far, let's say this is speed, this is position. This is what the relationship looks like. So when you cut the brakes off, you're going to slow down, but super slowly. So theoretically, you would never actually stop moving, but you would be going so slowly that it feels like you aren't moving. So then you have to pick whatever point you want to stop at. Like if you want to say, okay, stop is like 99% velocity gone. That is 3 standard deviations. Or you could say only 95%. That is 2 standard deviations. Or you could say like 67%. That's 1 standard deviation. So you just have to figure out, what do you want to call stopped? Now, I don't recommend testing this out with your car on the interstate or something, you know, unless you happen to run out of gas. But also, because there are other forces going on, like there's friction in your wheel bearings and stuff, there could be a side wind. Those things will play into the factor, and then your car will eventually stop. So if we solve out here for stopping distance, we'll call that D. So negative 2m over rho CD A times natural log of V over V initial equals D. So the reason you can't set V to be 0 is because there is no natural log of 0. It's not defined. So that's why you have to pick V being something else. So just choose it as something really small. If you say that stopping V is 0.01 times V initial, then the V initials cancel. So you just figure out like what percent of your stoppings, what percent of your initial speed do you want to consider stopped? And that's what you throw into here. So now it's interesting, like if you look at this math, it can just seem kind of complicated, but so I put it into a spreadsheet so that we can see how does the drag coefficient and the speed and the air density and stuff affect the distance. So we look at this sheet. So these charts show speed versus distance for air drag, and then drag force versus speed. So you can see the exponential relationship here. The force increases exponentially with the speed, and that's because F is proportional to V squared. So this is a parabolic relationship. F on the y-axis, V on the x-axis, F is proportional to V squared. And then for the speed versus distance, put in that logarithmic relationship, and you can see here, like with a low drag coefficient, it's going to go super, super far. But then with the faster that you increase the drag coefficient, like it makes a big difference of how far you can go once you cut the engine off. So you can see over here on the left, some of these parameters. So I have width, height. So these two are the like width and height of the vehicle. Combine those to get area. Then I put in air density, water density, vehicle mass, the velocity. So these are just different. You can change these numbers. So 30 meters per second, that's about 60 miles per hour. But let's say you were going 100 miles per hour. You can see the graphs look the same, but the numbers on the axes change. So we'll go back to 30. And then for water, you can see the graphs for water look exactly the same as the graphs for air, except that numbers on the axis will change because the fluid has a different density. So here in air, to get to essentially zero speed, say if your drag coefficient is 0.2, you can go to about 18,000 meters once you cut off the engine. But in water, if you cut that engine off, you cannot even go 25 meters. The water is so much more dense than air, it has so much more drag. So finally, we'll look at simulation of how all three of these relate to each other. So you can see here on one axis, we have drag coefficient going all the way from 0.2 to 1. And you can see that the drag force, which is here on the vertical axis, drag force is going to be 0, its speed is 0, no matter what the drag coefficient is. Because if the object is not moving and the fluid is not moving, then there is no drag force. But as soon as the object starts moving or the wind starts to blow against it, as we can see here on the speed axis, then the drag force goes up really fast.